So this is a video accompanying the introduction to the geometric sequences and series work. If you've looked at the notes already, you'll see that they start off with this example of the Australian Open men's single tennis tournament. Now there's 128 players in the tournament, and we're first asked to say how many matches are played in the first 3 rounds. Well, in this case, because it's singles, it's 1v1 game, so 128 players means if they're playing 1 against 1, that there'll be 64 matches possible in round 1. One person is eliminated from each game, so there's half the number of players in the next round. That means there'd be then 32 players, then there'd be 16 players, and so on and so on. So those are the number of games in each of the first, second, and third rounds. Then asks us, what do we notice? Well, of course, you can notice that it's halving, which makes a lot of sense if you think about the way that half of the players are eliminated because half the players have to win, half the players have to lose, so half are going home. Therefore, the number of matches each time is decreasing by a factor of a half. Then it says how many matches will be played in the last round. Well, the last round is the final, which is just one single game. So that's a pretty straightforward question. Then it says how many matches we played in total during the complete course of the tournament. Well, if we just carry this sequence on a bit further, we'll see that we get eventually down to here, and hopefully you can see the whole thing there. So 64, 32, 16, 8, 4, 2 and 1. If we add all this up together, that's going to be our answer. So we add all of these up, and we can use our GDC for that if we really need to. We should see that the answer is 127 matches. So that's just a real world example of what we're looking at here, which is a geometric sequence. So I could have written these numbers out going across the page in a normal sequence, and you'd see that they do have a sort of pattern. Now, if we just start the first few off here, 64, 32, 16, and so on. Now, it's not an arithmetic sequence because we're not adding or subtracting the same thing between each term, but we are doing something between each term. And in this case, we can see that what we're doing is we're dividing by 2, or another way of putting it, multiplying by 0.5 or by half. And that is consistent for every single term, and that would be carried on all the way through. When you're doing this, when you're multiplying by a common ratio, that is called a geometric sequence. Arithmetics when you're adding or subtracting the same thing each time. Geometrics when you're multiplying. So in the notes, it gives you the nth term for the geometric sequence. It's got some familiar parts to it. You've got un for the nth term there, u1 for the first term. We saw that with the arithmetic sequences. With r, which is a different term, we'll come to that in a second, and then this n-1 as the power. Just go through how that actually works in practice with our example. So the nth term is un equals u1, which is the first term, multiplied by this r, and then that is to the power of n-1. So we take the example of the tennis tournament for the nth term. Well, the nth term in this case would be given by the first term, which was 64 matches in the first round. And then to get to the next number of matches in the sequence, we have to multiply by this, which is the common ratio. It's just the number you multiply by to get to the next term, which in this case was 0.5. And the power is the number of times you have to do it. So if you want to get to the third, the fourth, the fifth term in the sequence, you have to multiply by this common ratio a certain number of times. But that certain number of times is n-1. You might remember that from the arithmetic sequence nth term. If we just remind ourselves of that, that's the same sort of thing. It starts with the first term in the sequence, but then you add on, because it's arithmetic, n-1 lots of the common difference. And you don't add n lots of the common difference, because if you're looking for the second term, you've already got the first term, and you just need one of these to get to the second term. It's the same sort of thing here. To get to the first term, you just got the first term. To get to the second term, you need to do this process just once. So it's the second term, but you do this only once. To get to the third term, you do this twice. So you have this n minus 1 there in the nth term. So let's look at the example that is given in the questions, which is here. And that's example 2. Example 1, there you go. So I won't go through every single one of these, but these are very typical kind of questions where you get given part of a geometric sequence and then you've got to work out the nth term or a specific term. So if we look at maybe just the first one together to get the idea, and then I'd like you to look at the rest of them. They all do work in a very similar way. So here you've got 4, 12, and 36, and you've got to work out the nth term and the 8th term. So it's obviously not an arithmetic sequence, but we can see that it is going to have this common ratio working between each term. Now in this case, it's pretty obvious what that's going to be, but there's a process we can use if we weren't quite sure. Because we're multiplying 4 by something to make 12, you can say that 4 times the ratio is 12, therefore the ratio is going to be 12 divided by 4, which is 3, as I'm sure you already knew. That means we can produce our nth term by just putting that into the general formula. So let's do that over here. Nth term is going to be the first term, 4, times the ratio, which in this case is 3, and we'll do that n minus 1 times. So therefore, to get to the 8th term, you do 4 times 3, 7 times, and then you would work that out. And the answer is given in the notes, which I'll have to look at, 8,748. The other ones work in the same way. Even if there's fractions there, it's still going to be this second fraction divided by the first fraction to work out the common ratio. So I'll let you have a look at those yourself. Now, one area in which this kind of maths comes up a lot, in which you'll actually have seen it before, is percentage change. Most common examples are compound interest. So you've got this set of formulas here, which at first might look a little bit confusing, but actually it really is just talking about how to find a percentage multiplier. So if we look at an example of that and then try and refer back to this formula and see if we can see how it works. So we take a typical compound interest question, like let's say somebody's got £5,000 and they put in a bank account and it increases by 15% each year. We'd multiply it by the multiplier of 1.15, and if it was happening for 5 years, we'd then do that to the power of 5. Well, this is actually a geometric sequence. It's got U1 sitting at the top here, and then it's multiplied by a ratio a certain number of times. Now, I'm going to be a bit careful with the power. Depending on how the question's defined, you might have the first year as being when they had the £5,000, which would therefore be U1, or maybe the first year is after this 15% has been applied. So it does depend on how that's worded. So in this case, I'd probably say that the nth term would be that, but it depends how the question goes. So where does this 1.15 come from? Well, if we start off with 100%, which is our original amount, and we want to increase it by 15%, of course that makes 115%. But we don't multiply by 115 because that would make it massively bigger. It wouldn't increase it by just 15%, it would make it 115 times bigger. So instead we turn that into a decimal multiplier by taking the 115, dividing it by 100, and that's where the 1.15 comes from. That's exactly what this formula here in the second part of the notes is saying. So the ratio, which is the thing you're going to multiply by, is given by this. Starting 100 and the percentage increase, so 100 plus 15 in our example, then divide by 100 to make it to multiply. And depreciation or decreasing works in the same way. If you're going to decrease by 15%, you multiply by 0.85 as you go through. Now, there's a couple of other examples. There's one about a car that is depreciating. I'm just going to let you go through that one yourself. Actually, the example's all in there. It works in a really similar way to what I was just saying. But I will show you example 3, which is this one about Snapchat. Very relatable. Not that I've ever used it, but it says that the daily users is found to be increasing by 2.5% per month. In May of 2018, the number of Snapchat daily users is 187 million. So determine the number of daily users in December 2018. So I sometimes get confused with these. You've got to be careful with how many times the ratio needs to be applied in this question. So we're starting off in May, and we're trying to work out the number of users in December, and it says every month you get an increase of 2.5%. So that means we start in May, and then we've got to go to June, to July, to August, to September, to October, to November, to December. So that's actually 7 steps. So that's why it says in the answer, the number of users in December is equal to the number of users in May times the ratio by 7, which is what the calculation is there. The bit I'm actually going to go through is part B, find the month of which year when the number of daily users exceeds 300 million, or first exceeds 300 million. So for that, we've got to set up an equation. So in this case, we know that we've got the first term, 187 million. We've got the multiplier, so it's increasing by 2.5% each month. And we don't know how many months it's going to go for, because that's what we're trying to work out. So we put that as n, and we know it's got to be bigger than 300. So this is an equation that we can solve using the GDC. So our unknown is going to be this x. I'm going to write it as an equation, because if we find the bit where it's equal to 300, then all we've got to do is just go a bit further than that, and we'll find the bit where it's bigger. So the way we'll solve it is by using the equation solver. So we'll go to equation, see that, okay, solver, just a regular solver in this case, so I'm going to press F3. I've already put it in there because I practiced this before, but you can see there 187 times 1.025 to the power of x equals 300. Press equals, make sure you press equals and actually press the solve button as well, and you'll see it comes out as 19.1423. So 19 months won't quite be enough. You have to go into the 20th month to make sure you actually get those 300 users. So 20 months you want. So you've got to work out then where actually you're going to be if you're 20 months ahead of May 2018. So I'll let you work that out. Another way of doing it though, which is always worth doing in this course, is graphing it. So go to the graph. Again, I've already put it in there, but 187 times 1.025 to the power of x. And if you graph this function, you'll see something like this. Now I've played around with the view window here, and I've got these settings. So we don't need anything below 0 on the x. I've gone 25 on the x for the max. For the y, there's no point going below 0, and we're going to go for max 400 because we're aiming for 300. So there's no point going much further than that. So that's my scale. I want to know what x value I'm going to get at the point at which the output, the y, is going to be 300. So I go gsolve, x calculation, stick the y in as 300, and then you can see there the same value. So 2 ways to solve that problem. The next problem is also kind of similar, using the same formula. So again, I'll let you have a look at that and see if you can figure out how it works. Try the other exercises. Do ask me via the Teams program if there's any questions about that, and good luck.